Okay guys, welcome. This is a continuation from the Transformers lesson the other day, which looked at real and imaginary numbers. We looked at polar and Cartesian form, and I've said that we would take on a little bit of a look at parallel RLC stuff. So just a quick recap. If we've got a resistor or a real component and a source of reactance, in this case it'll be inductance, XL, what we can do is we can represent that as real plus JXL. And in our previous example, the real was A, and that was, we called that JB. And what we said was that if we wanted to get this down to one source of impedance, we would do, which would look like this, Z. Z is equal to the real squared plus the imaginary squared, all square rooted. That'll give you the length of Z. But what we actually need as well as that, we need an angle. So what we would then do is, and again this is just a recap guys, what we then do is we do tan to minus 1 of the imaginary over the real, which would be tan to minus 1 of your XL over your RE, like that. Okay. And that's as far as we got, and well, we did a little bit more maths with it actually. We said that if you were going to do multiplication with this stuff, you would do that in polar, which remember is A at an angle of B. If you're going to do division with this stuff, you would also do that in polar, which again is A at an angle of B. If you're going to do addition with this stuff, you do, or subtraction, you do it in Cartesian, which is A plus JB. And again, with taken away, we use the Cartesian as well. Okay. If you want to know the rules of these, if you just refer back to the video before this on the same YouTube channel. Right, so the problem comes where we end up with two of these sources in parallel. So I'm going to start off with them converted to impedances already, because we went through that in the last session. And we said that we've got Z1 at an angle of θ1 and Z2 at an angle of θ2. And we want to reduce this down to one source of impedance called Z total at an angle of θ total. Yes, we want to reduce this down to, which remember this will form the equivalent circuit, which in this case would be one source of power, one source of resistance, impedance or reactance, and two sets of wires which are current carriers. Okay, so that's what we're trying to get down to. And we said that if we had resistors in this case, and those resistors were R1 and R2, we'd use a thing called product over sum, which is R1 times by R2 divided by R1 plus R2. The product on the top, the sum on the bottom, and you divide them. But because we don't have resistors, we've got reactances. It's the same rule, they're in parallel still. So it's Z1 times by Z2 divided by Z1 plus Z2. Now this leads us on to a little problem. Remember earlier we said that if we're going to do multiplication, so for the top bit, Z1 at an angle of θ1 times by Z2 at an angle of θ2. I know I'm not calling these the right names, please don't correct me in the comments. Divided by Z1 at an angle of θ1 plus Z2 at an angle of θ2. So this will give us our ZT at an angle of θt. Now, however, the problem comes where we've got multiplication on the top there and an addition on the bottom, and then a divide. So we want to do the top bit here in polar form, and we want to convert the bottom bit back to Cartesian. Okay, do the addition in Cartesian and then come back in polar form to do the division. So I'm going to show you this step now. We're going to put in some numbers, we're going to do it with the calculator, and we'll come back. Right, so say for instance we've got a source of our Z1 is 6 at an angle of 30 degrees, and our Z2 in parallel is 11 at an angle of 45 degrees. We'll just make these numbers up. Okay. So what we're going to do is we're going to need to do the top bit first, which is the multiplication, Z1 times by Z2. Okay. So remember, we do this in polar, and the rule is for that is we multiply the scalars and add the angles. So for this case here, it's going to be 6 at an angle of 30 degrees times by 11 at an angle of 45 degrees. So we multiply the scalars and add the angles. So it's going to be 6 times by 11 at an angle of 30 degrees plus 45 degrees. Okay, so in this case here, we're going to get 66 at an angle of 75. So that's the answer to the top bit here for the product over sum. Okay. Fairly simple stuff. We don't really need a calculator for that. The next bit, however, we're going to have to convert between Cartesian, between polar, and go back to Cartesian to do the addition, because if we try and do the addition in polar, it generates what I call the maths diamond. You start off with a small equation, and it gets bigger and bigger and bigger and bigger and bigger, and then you start to minimize that down to your answer, whereas doing the method I'm going to show you, it takes 2 seconds. Okay, so our numbers, let's keep that in shot there. The next bit that we're going to do is Z1 plus Z2. All right, so to do this, we're going to convert back to Cartesian. So remember, to convert from polar to Cartesian, we need a real, we need to end up with a real and an imaginary. Okay, and that's our angle 1, and that's our angle 2. So remember, the real is cos of the angle times by z, and the imaginary is sine of the angle times by z. So if we take our Z1 is 6 at an angle of 30 degrees, to convert that over to real and imaginary, our real one is going to be cosine of 30 times by 6, and our imaginary one is going to be sine 30 times by 6. So we'll do that on a calculator. Let's make sure that you're still in shot. So it's going to be cosine 30 times by 6, and that gives us 5.19. Should we call that 5.2? And our imaginary is going to be sine of 30 times by 2. Now remember, if you're using a Casio calculator with this, you can just tab backwards and just change that cosine for sine, saves you typing it in both times. Unfortunately, I left my calculator on my desk at work, so I'm having to use this app, and that comes out at 3. Remember, that's going to be a J3, isn't it? Because that's imaginary. So we now know that Z1 is 5.2 plus J3. Okay, that's our Z1. We do exactly the same thing for Z2. So Z2 is 11 at an angle of 45 degrees. So to get our real imaginary from this, we say that our real 2 and our imaginary 2 are cosine of 45 times by 11 and sine of 45 times by 11. So again, we use our calculator. So that comes out to be cosine of 45 times by 11. And that gives 7.77. And we do exactly the same thing for our sine. Sine 45 times by 11. And that gives us exactly the same number. I think I'm just going to do that again to make sure I haven't put that in wrong. Cosine 45 times by 11. No, yeah, they're both 7.77. That's, which would make sense because at an angle of 45, our real and imaginary are going to be exactly the same, aren't they? 7.77, and that's a J. So for this one here, our Z2 is going to be 7.77 plus J 7.77. Just a quick sort of recall why that is. If this here was an angle of 45, it's an equal distance between there and there, any point on that line. If this was to lower, then obviously this line will become longer than this line, and if this was to go higher, this line will become longer than this line. Because it's 45 degrees, it's exactly in the middle. Right, so we've got our two values there. What we do now is, we say, well, we've got 5.2 plus J3, and we've got 7.77 plus J 7.77. We want to add these together. Now, if you remember the rule for adding Cartesian, it's add the real and then add the imaginary. So there's a couple of ways of doing this. I like to stack them on top of each other. So I know that my reals are in one line. Sorry, I've got my little 5-year-old off with me at the moment, if anybody's wondering what that whistling sound in the background is there. So 5.2 added to my 7.7. So the equation will look like plus 7.77 plus J3 plus 7.77. And where that's come from is obviously 5.2 is there, your 7.7 is there. That 7.7 comes down to here, and your J3 comes down to there. Yeah. So 5.2 plus 7.7, I've been off work far too long now to be able to do that in my head, I'm ashamed to say. That gives us 12.97. And our J is going to be 10.77. Okay. So now that's what is on the bottom of our equation. But we can't divide using Cartesian numbers. Remember, because you multiply and divide in polar, you add and subtract in Cartesian. So we need to convert that back. And to do that, we just use a little bit of Pythagoras' theorem. So remember, this is your A, this is your JB. So to get our Z, back to Z, sorry, that would be...
That's where the Queen lived.
I hope everybody else listen to this, by the way, are stuck at home with children equally like I am, so you all have to suffer in exactly the same way. So yeah, so this becomes a value of Z. So our Z equals the square root of A plus the square root of JB. Actually, it's just B because we're not putting a J under this thing. And that will give us our value. And then our angle will be tan to minus 1 of the imaginary, which is B, over A. Okay. So in this case here, it's going to be 12.97 squared plus 10.77 squared, all square rooted. And then our angle is going to be tan to minus 1 of 10.77 divided by 12.97. And that gives us, if we put that into a calculator, we've got 12.97 squared plus 10.77 squared equals, and then if we can square root the answer, plus that gives us 16.85. If anybody can remember when they were back doing GCSEs and you had a teacher like mine that would say, the way to check that is that number should always be bigger than those two numbers. Not those two numbers combined, but that number should be bigger than the biggest number out of those two, because obviously it's a hypotenuse you're calculating. So yeah, and then our 10 to the minus 1 of the imaginary over the real, which is 10.77 divided by 12.97. So that gives us an angle of 39.7 degrees. So now we can do our division. Okay, so we can look at our original number. So our original top part, remember it's we're now doing them divided by each other, so it's 66 at an angle of 75 divided by 16.85 at an angle of 39.7. So remember the rule for this one. Again, if you don't know what the rules are, go back to part 1 of this video and you'll be able to see where did the addition and subtraction and multiplication and division. When we divide only in polar numbers, and the rule is you divide the scalars and take away the angles. So in this case here it would be 66 divided by 16.85, and that'll give us the scalar. So 66 divided by 16.85 gives us 3.91. Sorry, my little boy's dead excited to make a cake. Yeah, again, I hope all of you are suffering in the same way I am. And then the angle is these two taken away from each other. So 75 take away 39.7, and that gives us 35.3 degrees. So the total impedance for this whole circuit is 3.91 at an angle of 35.3 degrees. So that's how you do it. That's how you do the calculation to get down to one source of impedance from a parallel circuit. Okay, so just a quick recap. You multiply the top and add the bottom. You multiply the top in polar, you convert the bottom to Cartesian, do the addition, then convert back to polar, and then you do the division that way. So you just divide the top by the bottom to get the total. One more note: if you're asked to do a current calculation with this, remember the magnitude of that'll give us our Z. And if you want to work out current, what you do is you divide the original supply voltage by it. So say, for instance, my original supply voltage for this was, let's just make something up, 330 volts, sorry, because I've already written a 3. So say if our original voltage was 330 volts, it would be 330 divided by just the magnitude. All right, and that will give us the current for our circuit that will be flowing through our circuit. So 330 divided by 3.91, that's going to give us 84.39. That's quite a lot of current. Be somewhere else if that's flowing, I think. Amps. It doesn't matter what the angle is, but you could say that the angle is plus 35.3. That's leading, so the current's leading. But to be honest with you, if you're ever asked to do this in an assignment, you can just leave that bit off. I'm not really interested, because if I'm just asking for the magnitude, it's just that value there. Okay guys, any issues at all, drop me an email. You've all got my email address. And if there's any questions or any queries that you think can wait, drop us a comment below. Could I please ask that the students viewing this give me a like and a subscribe, just to stay in touch and see other videos that I'm posting. Yeah, and have a good day. Bye.